I will begin. We begin with a word of prayer. Okay, I'll begin. Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you bless our work, help us to glorify you what we do, and just pray that you'd encourage the students if they're struggling, just to do their best and to rely on you, Lord. In your name I pray. Amen. Okay, so let's talk about exponentials and logarithms. And so I'm going to share with you guys some of the, important properties of both. And just to start with, I'll work an example. So example 1, let's graph y equals, let's say, 1 plus 2 to the x minus 3. All right. So the way I would graph such a thing as this is I would think about y equals 2 to the x. That has a graph that basically looks like this, right? It has a y-intercept of 1. So this point right here is, let's say, 0, 1. And it's got a point over here of 1, 2. And it's got a point, if I go over here further, it's got that point of 2, 4, right? So if I'm going to take that graph, and what am I going to do to get the graph that I'm interested in this example? So y equals to 1 plus 2 to the x minus 3. I should do what? Up 1, right 3, right? And so that's pretty much all I got to do. So let's see here. There was a horizontal asymptote for the original one of the x-axis, right? So this is like the original. It's mostly this way I'm talking about, right? So that gets shifted up 1. Right? And let's see here. The y-intercept point, I'm going up 1 and over 3, so it shifts from 0, 1, it shifts to 3, 2, yeah? So 1, 2, 3, so like there. And then this 1, 2 shifts to where? 4, I think. Because I go up 1. I'm sorry. I go up 1. I can't do math. 2 plus 1 is 3. Going right 3, so yeah. This is 3, 4. So I go to 4, 3, something like that. And then when I get to 5, I got this point up here, right? So something like that is the graph, and it looks kind of sort of like this. I was trying to hit that point, but you get the idea. Okay. So there's your y equals 1 plus 2 times x minus 3. Now, if I call this thing f of x, what's the domain in the range of f? Yeah, the domain, that's easy. Minus infinity to infinity, it's just everything. What's the range? 1 to infinity. Is 1 excluded, included? What's the story there? I hear the ooded. I didn't hear the start of the word. Included. Ooh, no. 0. Excluded. Yes. So we want 1 to infinity. And the reason being is we never do get to the green dotted line, we just get closer and closer to it. Basically, the formula, it's 1 plus 2 to something. 2 to something never is 0. So you always have at least 1, and you're adding something positive to it. So you get closer and closer to the green dotted line, but you never get to it, so 1 is not included. Okay, so now I would say, to be fussy, that this is not an exponential function, all right? Because exponential function means a very specific thing to me. So definition, if f of x equals a to the x for a greater than 0 and a not equal to 1, then it's an exponential function. Right? Exponential function. Now, furthermore, f inverse of x is called log base a of x. Is called log base a of x. Log base a of x. Or you could say f inverse is the logarithm base a. All right, it's a function. It's the inverse function of the exponential. Now, I say a greater than 0, a not equal to 1. In practice, I almost never talk about fractional bases. Like, you won't find me talking about log base 1/2 in class. It's not something I'm interested in. It's nothing I ever want to graph. I don't care. Sorry. We have bigger things to worry about. So I'm mostly going to focus on the case that a is, I'll just say this, remark, if I'm talking about logs, if I'm using log base a, probably a is greater than 1. Technically speaking, you can define log base 1/2, but let's not. Now, what do the graphs of these different things look like? Let's talk about different choices of a for a bit here. So I have got the projector out for other sections today, and I think it added pretty much nothing to the lecture, so I'm not going to do it in here. And so let's just graph. So if you look at this, we can graph, here's y equals 2 to the x, let's say. All right. And so we can just track a couple points that are kind of points of reference. Here's, 1, 2, and over here, if I did it right, it would be the point, minus 1, 1/2. That's the 2 to the x function, all right? What does 3 to the x look like? 3 to the x, kind of the same shape, but it's bigger over here. The point right there is not 1, 2, but 1, 3. And over here, it's below, like that. And the point right here, when instead of being minus 1, 1/2, you'd have minus 1, 1/3. And if you study these graphs, all right, if you study them carefully, and I got out the Desmos and we looked at it and stared at it for a bit, you could figure out that the slope of y equals 3 to the x at x equals to 0 is larger than 1. And you could also observe that the slope of y equals 2 to the x at x equals to 0 is smaller than 1. Now, we haven't, and you don't, and we will not define slope in here. I'm using it as a conceptual term. What do I mean by slope of a function? I'm using that to mean the slope of the tangent line to the function. What's a tangent line to a function? Well, we don't have a careful definition in here because this is not calculus, but it is nevertheless something you can think about. The tangent line is just, if you were to imagine taking a line, right, and making it line up with a function close to the point, it would be like this. So like my 3 to the x, see my 3 to the x curve? It's got a tangent line that's kind of sort of like this, yeah?
Is that linear regression?
It is not linear regression, although it is related. It's the best linear approximation to the function. So look, the tangent line to the purple is kind of like this. The tangent line to the red, it's kind of like that. And if I did it carefully, you could see that the slope of the steeper line is bigger than 1, and the slope of the shallower line is smaller than 1. What that means is that there is some choice of base between base 2 and base 3, which will have slope 1 as it goes through the y-intercept, right? There is something in between. There's a middle ground. I'll draw it in green, like so, that if I was to carefully graph that in there like that, this guy has slope 1 at the y-intercept. That particular choice of base, the base for which the slope of the tangent line at 0 is 1, this is what we call the exponential. The exponential. So this actually is y equals what's called e to the x. All right, y equals e to the x is the special base which has slope 1 at the origin. So this e here is approximately 2.718 blah, 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 blah. This e is in honor of a dude named Euler, long since dead. He was a very important 18th century mathematician. He's really arguably the first, maybe one of the first mathematicians to really do algebra and pre-calculus in kind of more or less the same way we do it. He popularized many of the ways of thinking that we think about things still, and also the notation that we use. A lot of it is descended or directly his notation. So, I mean, he's very influential. A lot of what we use is due to Euler. And so we honor him with this choice of E for base E. All right, and I would say that, you know, y equals e to the x is, you know, this is the exponential, because it is the most important one, okay? So if you hear a mathematician talking about an exponential function, right, odds are what they mean is this one. This is the one we care most about, because it's got that special property of slope 1 at the origin. And it also appears in all kinds of sorts of formulas for science and engineering, right? If you've studied population growth or like bacteria decay, all these sorts of things, all those kinds of formulas can be written with e to the x. I mean, okay, fine. In truth, they could also be written with 2 to the x. It's really kind of a matter of taste, but it is nevertheless an important thing. Now, in the particular case, we have other special notation. So log base e is defined to be natural log. So this is the natural log. There's also log base 10. This is usually just called log. So this is the so-called common log. There is also log base 2, which is typically noted LG. I don't have a good name for that, but it comes up if you're studying, you know, base 2 things, which of course, if you're a computer scientist, you might want to do that, yeah? Binary. Yeah, binary. Okay, so there you go. What are the properties of the exponent and the log? So let me just rattle them off right quick for you. Properties, and then we'll try to solve a bunch of problems. So, of course, first and foremost, we should remember that the log base a of a to the power, you know, I'm going to use s here. S is equal to s again. If we have a to the log base a of t, we get t again. All right, they undo each other. if we have log base a of st, it's log base a of s plus log base a of t. If we have log base a of s over t, we have log base a of s minus log base a of t. There is also this property, log base a of s to the power p is p times log base a of s. These are all properties of the logarithm. There are, and I really should have probably not started with this. I probably should have started with what I'm about to write over here, because each one of these, the reason that they're true, it's because there's a corresponding property, a law of exponentials, which you guys of course know, right? You guys know the laws of exponentials, yes? I think you do, but you may or may not be confident about them. So let's write them out here. So like a to the s times a to the t is a to the s plus t. There's that. There's also that a to the s over a to the t is a to the s minus t, right? I think we did a little bit of this like week 1. And let's see here. Also, we have a to the s raised to the p power is a to the s times p. You do that. That's another one. All right. And then there's other things that you kind of take for granted but you forget about. Like a to the 0 is 1. Or a to the 1 is a. Or a to the minus 1 is 1 over a, right? Now those, the corresponding like log properties, like the last 3, we have the following. We have like log base a of 1 is 0. Log base a of a is 1. Log base a of 1 over a is equal to minus 1. So these things are all true. And, you know, it would be good, of course, if I derived them for you, but I think we won't do that today, all right? But we can prove these properties, and we probably should, because it's a good exercise, and it will make you think about things a bit. Let's solve some problems, though, instead, if you guys don't mind. So, example 2. So what follows here, I'm going to use these properties to simplify things, to calculate things, okay? So suppose I have 3 to the x, let's say 3 to the, well, 3 to the 2x equals to 1 over 81. Can we solve this? Well, I think we can. So everything here is actually kind of like base 3, right? Like 3 to the 1 over 81 is actually what? 1 over 3 to the 4th power, right? Because 81 is 9 times 9, which is 3 squared times 3 squared, which is 3 to the 4th. Or if you like, 3 times 3 times 3 times 3 is 81. So, hey, one way I can solve this problem is simply to take log base 3 of both sides. Let's try it that way. Take log base 3 of both sides. What do you get? If I use my properties of logs, this on the left-hand side simply simplifies to 2x. On the right-hand side, I've got log base 3 of 1 minus log base 3 of 3 to the 4. And what's log base 3 of 1? So this is 0. Okay, that's 0 because 3 to the 0 is 1. And this one here, it's 4. by definition of the log. So what we got is 2x equals to minus 4, which gives us x equals to minus 2. So I solved this problem by taking the logarithm of both sides, okay? This is a technique for solving an exponential equation. If we have an equation which is based on exponentials, often if we take the logarithm of the equation, it solves it kind of nicely. There is another way to do this problem. Do you guys know what it is? What's an alternate method? How about this? This is really 3 to the 2x equals 3 to the minus 4, is it not? Can you recognize? That's what this equation is. And then by the one-to-one property of the 3 to the power function, right? We have let me just write it this way. A to the x1 equals a to the x2 implies x1 equals to x2, right? This is the so-called one-to-one property of exponentials, right? So this, we can use this if both sides have the same base, right? And there's no pluses and minuses, no funny business, just straight up a to, a base to a power equals that same base to a power. When we have that, we can just equate the arguments. See, this gives us 2x equals minus 4, which of course gives us x equals to minus 2. Which is the right way to solve this problem? The what? The blue way? Yeah, both are correct. Yeah, I think that's right. I think the way you're comfortable with is the right way, right? It's wise to be able to do both, of course. Example 3. Let us solve this one's kind of persnickety. I tried this. This one, I made a stupid mistake on this in the last section. Let me try it again here, see if I can do better. 5/3 to the x equals 27 over 125. It's a problem that we're supposed to solve. So, look, the one way you could do this would be to go, okay, well this is really, obviously this is 3 to the 3rd power over 5 to the 3rd power, right? And so we could also look at this as 3/5 to the 3rd power, yeah? And then here's the kind of sneaky step. That is equal to 5/3 to the minus 3 power.
Why is it the minus 3?
If I have, let's try it out here. A over B, right, to the t power, right? I can rewrite that as, 1 over, well, A over, I can write that as B over A to the minus 1 power to the t, right? Because B over A to the minus 1 power is equal to, 1 over B over A, which you could recognize, however you want to understand that. Okay, the reciprocal of the reciprocal is the fraction again, yeah? So, and then this is what? This is B over A to the minus t power. So if you want to flip it, you have to change the exponent to minus is the quick rule. If you don't want to think through all this, you can just remember this is equal to that. That's a nice, just quick rule of algebra to know about. So with that, I have 5/3 to the minus 3, right? And then we can look and go, oh, okay, so this and this are equal by the one-to-one property. X equals to minus 3, right? So it's kind of anticlimactic, isn't it? Now, what if you don't have this inspiration to rewrite the number on the right-hand side as a power of 5/3? I would argue that that's actually kind of clever, right? Is there a less clever way to do this? So let me show you brute force solution. So we have 5/3 to the x power equals to 27 over 125. Right? When I have something like this, my natural inclination, outside the world of carefully crafted and contrived college algebra problems, if I have an equation like this, I take the natural log of it. That's what I do. So if I take the natural log of both sides, that will be a very productive thing to do, because what I get from that is x times the natural log of 5/3, yeah, equals to, the natural log of 27 over 125, yeah? Which then gives me x equals to the natural log of 27 divided by 125 divided by the natural log of 5 over 3. Right. Now, if your annoying college algebra teacher tells you something like simplify your answer, you've got work to do here, but it's simple enough work, right? You can be systematic and kind of unravel these things one piece at a time. See, because this is the natural log of 27 minus the natural log of 125 divided by the natural log of 5 minus the natural log of 3. What is the natural log of 27? The natural log of 27 is the natural log of 3 to the 3, and minus the natural log of 5 to the 3, right? Divided by, well, log 5 minus log 3. But we pull 3 out, we get 3 log 3 minus 3 log 5. Factor out, and you've got minus 3 times log 5 minus log 3 divided by log 5 minus log 3. But those are equal, and so the answer is minus 3. This is brute force because it's not clever. I'm just applying properties of logarithms systematically towards the goal of simplifying the answer and finding the answer. Obviously, rewriting the number as a power of 5/3 is much easier. The clever solution is almost always easier, right? But if you don't see the clever solution, the idea, oh, I can take the natural log of both sides, is a very productive thought. Yeah.
So what if you don't have nice numbers?
If you don't have nice numbers, then your answer is probably going to be in terms of natural logs of some ugly answer, some ugly number, more often than not.
If you don't have a 27, 125, but have instead 29 over 130.
27 over 1. I mean, if they're not related in this way, then you're not going to get a nice number. You're going to get natural logs of something complicated as your answer.
Okay.
Yeah.
So you would do it the brute force way?
Yeah, sometimes the brute force way is the only way. Like, for example, yeah, question?
So the beginning, you get 5/3.
Yeah.
Where do we get all the other numbers from?
These numbers?
Not like the 27 over 125, like the first one.
It's given.
That was the starting. That's the problem statement. Solve like the. No, that's, that's a very good question. So like I forget sometimes, but I should start by like this, solve. Like solve it, that's the problem, yeah. Good question. Now, you know, I will say this, the higher level of the mathematics I teach, the less my presentation becomes about problem solving. At some point, I give you examples which are just about exploring a mathematical idea. Like, it doesn't always have to be solving a problem. Sometimes all of the steps in the example are the point. We're just exploring the different properties at play, but that wasn't the case for that example. Let's work another. So here's one where you can't get rid of the natural log. Like it is what it, yep.
During the quiz or test, would you be able to use a calculator to
Oh yeah. Oh yes. You should have a calculator for the natural log. Although there are also problems which you should be able to solve symbolically, right? Like what example was I on? 5? I'm on 4? Okay. So example 4. So like there are relatively simple problems that you can't help but have natural logs in the answer. For example, you get something like this. 2 to the 3x minus 7 equals to, oh, I don't know, 5 to the, you know, minus x squared. There.
Wow.
See, this is actually easier than example 3. Partly because it's just not going to have a pretty answer. There's no pretty answer to search after. But the answer's not too bad. Let's see how it goes. So the first thing we must know is laws of exponents, which is that this is just 5 to the minus 2x. Okay, so let's get that out of the way. Next up, I take the natural log of the equation. That's my next move. So natural log of 2 to the 3x minus 7 equals natural log of 5 to the minus 2x. And now I use properties of the logarithm. So the power property, I pull out the 3x minus 7 times the natural log of 2. On the other side, I get equals to minus 2x times the natural log of 5. Now I solve for x. So I've got 3x log 2 plus 2x log 5 equals to 7 log 2. I moved all of my x's to one side and all of my everything without the x to the other side. Now factor the x out. And solve for x, yeah? So there you go.
So what's the number? What's the number?
You got a calculator?
So whenever we are on this, do we give that or do we give this the calculator answer?
Depends on the instructions. Like, I could make it worse. So leave answer as ratio of ln's. So write the answer as the natural log of something divided by the natural log of something else. Can you do that? I'll do the easy part. Natural log of 2 to the 7. Oh, okay. That's right. I try to harass people when they're leaving, but sometimes it's, let's see here. If you're coming back, then it's different. All right, so log of 2 to the 3 plus log of what? 5 to the 2, yeah? But what are the properties of the natural log? Well, I mean, so the numerator's done. That's natural log of, let's see here. 2 to the 5th is 32, 64, 128. That's the natural log of 128. And downstairs, we multiply these guys. So that's 8 times 25, which I think is 200. So natural log of 200. So if I was thirsty for points, if I wanted to, you know, water the ground with the points of college algebra students, tears, if you will, I would ask for the answer to be given in this format, as it would stop many of you in your tracks, which is not my goal, but sometimes I inadvertently do this, you know. But if we understand properties of logs, we can convert things like this to things like that, yeah? But that is, this, what I just wrote in red is itself kind of a separate problem, right? But this is one of the things we're after. We want to understand how to convert one expression with logarithms to another and understand when they're equal, even when they don't appear equal at first glance. Now, if I want to be lazy, if I'm going to be a lazy instructor, how would I want my answers? I should ask everybody to give me answers as decimals to three digits carefully, right? Because you can always get your calculator out and you can compute whatever you like here, and you should get the same number, right? Like I can do it. I got a calculator here somewhere. Where did I put it? Oh, no, it's okay. I thought I already had it out, I'm just remembering last class. Let's see here. Natural log of 128 divided by natural log of 200. What you got? I got 0.9158 approximately. So there you go. I mean, but if I want an exact answer, then what I wrote in red is better, yeah? Okay, let's look at another one here, guys. So there's a mixture of problems in your homework, right? There are some that you probably need to solve with this take the natural log of both sides idea, right? But there's a lot of other ones that are really geared towards using like the one-to-one property of exponentials, essentially. So, you know, if you can use the one-to-one property, that's nice because you don't have to pick up your calculator, right? So I should mention something else, change of base. Let's derive the change of base formula. And here's what I mean, one thing I mean by that. Suppose we want to write a to the x as e to the something. What something should I put there? What should I put y equal to in order to get, can I rewrite a to the x as e to the something? Can I do it, right? Well, check it out. Take the natural log of both sides. What's the natural log of e to the y? Well, natural log and exponential, these are inverse functions, right? So that just gives me back y again. And so, oh, there it is. A to the x equals to e to the natural log of a to the x. But I can do better than that, right? What is natural log of a to the x? I can pull the x out, right? So that's e to the x log a. So here's a kind of a fun formula. A to the x we can rewrite as e to the x times the natural log of a. So any exponential function can be repackaged as a, the natural exponential times the log of the base. An application of this, example 5, would be this. if I've got, say, 2 to the power t, I can rewrite that as e to the t times the natural log of 2. You may have run across this if you've studied like doubling time problems in chemistry or something. Sometimes this shows up there. Okay, anyway. There's also a change of base for the log. And here's how it goes. If we have log base a of x, we can rewrite that as the natural log of x divided by the natural log of a. Okay, more generally but less usefully, that's also log base b of x divided by log base b of a. So these are the change of base formula. For the logarithm. And this is like pretty important because if you're like me, you can't figure out how to use the log base 7 on your calculator. Like, there is a log base 7 in this thing, but I don't know how to use it. You know? Like, I hit the log button and it just shows up log. So, and what is that log? That's actually the common log. If I just hit log. If you're ever in doubt about what log you're working on, so like example 6 for a second here, just this is a real low-tech one. But if I calculate common log of like 1,000, what should it be? (10 to the 3rd power, right? But common log is log base 10. So by the definition of logarithm, that's 3. So, you know, if I calculate, I've got log here, and if I plug in 1,000, what should I get?
Give 6.9.
I get 3.
What?
If I do natural log of 1,000, that will give me 6.9, yeah. 6.90777, so I'll say 6.9078, right? Approximately. All right, so there's that. So, like, how are these related? We could see the change of base formula in this. So, like log of 1,000, we could also write as like, you know, natural log of 1,000 divided by the natural log of 10, because this is log base 10. Now the natural log of 1,000 is 6.9078-ish. The natural log of 10 is 2.3026. And so if we multiply those, divide those numbers rather, I get 3.0001. So, because I wasn't careful to keep enough digits, you know. Okay. So, kind of a more interesting, more reasonable example here would be something like this. If I wanted to calculate log base 7 of, you know, 20, or let's say log base 7 of whatever, 13, okay? Then the way to calculate that with most calculators is, you know, natural log of 13 divided by the natural log of 7, whatever that works out to you. Now, I think if you study my calculator, the Casio FX115ES, carefully, it does have a log base 7 function in it, but I don't currently know how to get the buttons to work to make it happen, you know? So anyway, so I'm kind of stuck with the change of base formula way of doing things at the moment. Log 13 divided by log 7, what do I get? I get 1.3181 approximately, okay? Any questions about this? So this is important because you might want to calculate the decimal form, of a logarithm of a weird base, and this is kind of how you have to do it, right? So let's look at some other examples. Do some rapid fire examples here, yeah? Finish example 5? That is it. Yeah. So example 8, we're going to solve 256 to the 3x equals to 64 to the x plus 2. Example 9, we're going to solve 1 over 16 equals to b to the minus 4. And this will be the final example for today. Example 10, we're going to solve the square root of 2 to the x plus 8 equals 4 to the x. And we're not going to need natural logs for any of these. These we're all going to solve with the one-to-one property of the exponential, because these are all same base formulas. Like, both sides can be put into the same base. You just got to see it. And so like here, the base is 8. What's 256 in terms of power 8? I'm going to say base 2. So like 2 to the 2 to the 8th is 64. 2 to the 9th is 128. 2 to the, am I wrong?
Yeah.
That was what? 2 to the what? 2 to the 6 is 64? Is that right? I mean, correct me, that's fine. 2 to the 7th, 128. 2 to the 8th is what? 256? Okay, so what I have here is 2 to the 8th to the 3x power equals 2 to the 6th to the x plus 2 power, which gives me 2 to the 24x equals 2 to the 6x plus 12, which then gives me 24x equals to 6x plus 12. Therefore, 18x equals to 12. Therefore, let me say implies, which then implies, of course, x is equal to 12 over 18. So that's how you can do that problem. The next problem is easier, right? Because this is what? 2 to the minus 4 equals b to the minus 4. I said we were not going to use logs. Maybe we should use the log here, though. Yeah? If I take the natural log of both sides, what happens? We get minus 4 natural log of 2 equals to minus 4 natural log of b. The minus 4's cancel, and that gives us natural log of 2 equals natural log of b, right? But the thing is, the natural log is a one-to-one function. Or if you like, take the exponential of both sides now. E to the log 2 equals e to the log b, which gives me 2 equals to b. Right? Or, of course, you could have gone back to this initial step right here and said, oh, well, an obvious solution to this is to put b equals to 2, right? But if for some reason you didn't see that, you can hit the equation over the head with the natural log and then undo that with the exponential like I just did. This one here looks like base 2 is our friend, yeah? So this is 2 to the 1/2 to the x plus 8, yeah? Equals 2 to the 2 to the x, which gives me 2 to the x plus 8 over 2 equals 2 to the 2x, which gives me x plus 8 over 2 equals 2 to the 2x. Multiply by 2, I got x plus 8. I'm doing your homework for you guys. Equals to 4x, so do pay attention. 8 is equal to 3x. X is equal to 8/3 apparently. So anyway, these are some rather large hints for your homework. I don't have a color printout, so I can't really tell if these are randomized or not. I may have actually just literally solved a few of your homework problems, and if so, I'm sorry. I've deprived you the struggle. The struggle is how you learn, right? No struggle, no learning.
No pain, no gain.
No pain, no gain. Yeah. Anyway, thanks guys.